6.1a is on simplifying nth roots. So roots or radicals are what Unit 6 is all about. And the important thing to remember about roots and radicals is that they are the opposite of exponents. So this unit is the opposite of our exponent unit. So for our roots and radicals, we have two numbers we have to review. We have irrational numbers that can't be written as a fraction. So these are like non-repeating decimals like pi, or roots when the radicand is not a perfect square. So for example, we can't take the square root of 2 because it's not the perfect square. So if we were to take that, we would get an irrational number. Rational numbers can be written as fractions. Right? So anything that can be written as a fraction. The decimals repeat or terminate, so that means it ends. All the integers are rational numbers, so that's all your 1, 2, 3, 4, -1, -2, -3, -4, etc. And roots when the radicand is a perfect square. So for example, the square root of 4 is equal to 2, so that would be an example of a rational number. Now, radicals. We've already used a few of these vocabulary words, but radicals are referred to roots. So if you hear roots or radicals, they're referring to the same thing. And a radical is asking you what times itself, the index number of times, equals the radicand. So if we're looking at our little diagram here, we're looking for the number that if we multiply it by itself, in this example, if we multiply it by itself 3 times, we should get 8. So this little kind of check mark with the line on top of it, that is our radical symbol. Anytime you see that, that's talking about radicals or roots. The number on the outside, right, this is telling us, it's called the index, and it's telling us what root we're taking. Usually we take the square root, but we could take the cubed root, or the 4th root, or the 5th root, or the 100th root, whatever we want. And then the number under the radical symbol is the radicand. Okay, so again, radicals are asking what times itself, the index number of times, equals the radicand. So this example is asking what times itself 3 times equals 8. Well, if we think about 8, that's 2 times 4. 4 is 2 times 2. So 2 times itself 3 times equals 8, which means that the cubed root of 8 is 2. So that's what we're practicing today with our radicals. So our job is to put radicals in simplest radical form. So there are 3 rules we have to follow. There are no perfect squares in the radicand. So that means if we had something like 25, we would have to simplify that because that's a perfect square. There are no radicals in the denominator. So that means if we have a fraction, like 1 over the square root of 25, we can't leave it like that. We have to get the radical out of the denominator. And last but not least, there are no fractions or decimals under the square root. So if it was your job to take the square root of 1/25, again, you couldn't have that fraction in your radical. So those are our 3 rules that we're going to follow. Let's practice. So we want to simplify each expression. So the problems we'll be looking at are not going to be perfect squares. Keep that in mind. So letter A says we want to take the square root of 90, but 90 isn't a perfect square. There's not one integer times itself that will give us 90. So we're going to factor 90 in order to figure out how we can simplify this, or if we can simplify it at all. And we're going to follow these rules. Now for this one, we don't have to worry about a denominator because it's not a fraction. We don't have a fraction or a decimal under the radical, but we do need to make sure there are no perfect squares in the radicand. So we're going to start off just by factoring. So, well, what would be 90? 9 times 10 would be 90. Okay, well, I'm going to keep factoring. 3 times 3 would be 9. And 2 times 5 would be 10. Notice how I can't factor 3 and I can't factor 2 or 5 anymore. When I can't factor anymore, that's how I know I'm done. Now looking at these numbers, we're looking for groups of 2 because we're taking the square root. So here's a group of 2, and that's our only group of 2. So 90 is really the same as saying we have 3 squared times 2 times 5. So remember we were talking about opposites. So our radical is the opposite of our square root. So really fast, just a side note here, if we had 5 squared, that would be 5 times 5, which is 25. If we want to take the square root of 25, well, that means we're taking the square root of 5 times 5, which is the square root of 5 squared. And since these are opposite, they undo each other. It's like adding $5 and then subtracting $5. You end up with 0. Okay, you end up with nothing having happened. So if you square something and then take the square root of it, nothing changes. So you're just left with whatever number was in there. That's why we're looking for groups of 2, because if we find groups of 2, then we just get to simplify. So looking at the square root of 3 squared, well, these are opposites. Since they're opposites, they cancel each other out. Now, notice how when they canceled it out in our example up in the corner, our radical disappeared. So what happens when it cancels out is that the 3 is no longer under the square root because we evaluated the square root, right? If you have 5 plus 2 and you get 7, you don't keep writing the plus sign because you computed the operation. So now that we've computed this operation, the 3 gets to come out of our radical. Now, our 2 and our 5, notice that those are not a group of 2, and so those are stuck in the radical. Those are stuck there forever. We can't get them out. They just stay. And remember, 2 times 5 is 10. So our simplified problem would be 3 times the square root of 10. So that's what we're doing here. We are simplifying our radicals. We are trying to get them to be in their simplest form. So looking at letter B, the square root of 192, we're going to start off the same way. We're going to start by factoring it. Well, it's even, so that tells us that we could take 2 times 96. Well, we're done factoring 2. Well, 96, again, it's even, so we could take 2 times 48. For 48, we could take 6 times 8. 6, we could take 2 times 3. 8, we could take 2 times 4, and 4, we could take 2 times 2. So we factored the whole thing. And now we're looking for groups of 2. Keep in mind that once you factor, I factored 96, so I don't care about that anymore. I factored 48, so I don't care about it. I factored 6 and 8. I factored 4. After you factor, you're just looking at your numbers that are left over. So we have a group of 2 right here. We have a group of 2 right here. Here's a group of 2. So we could write the square root of 192 as 2 squared times 2 squared times 2 squared times 3. And then we would just take that square root. Remember, these cancel each other out. All 3 of these cancel each other out because that square root is the opposite of squared. So that means we're going to have a 2 from right here times another 2 times another 2 that comes out of our radical, and then that 3 is stuck in that radical forever because it doesn't have a group of 2. And then after you simplify, you need to make sure everything that you can multiply together is multiplied together. So 2 times 2 times 2 would be 8, so 8 times the square root of 3 is our answer. This is what we're looking at for radicals. Basically, you factor and you figure out, well, what can you simplify? What can you take out of your radical? We have a couple more examples. So looking at letter C, it'd be a good idea to pause and see if you can solve this one for yourself. Again, we're going to start by factoring since it's not a perfect square. So 3 times 25 is 75. 5 times 5 is 25. So that tells us we have the square root of 5 squared times 3. Well, the square root of 5 squared is just 5. And we can't take the square root of 3. So that is our simplified answer. Again, it'd be a good idea to pause and try letter D. Well, 5 times 25 is 125. 5 times 5 is 25. Remember, we're done with that now, so we're just looking at 3 5s. So we could write this as 5 squared times 5. Again, the square root of 5 squared, those are the opposites, so we just have a 5. And then this 5 is stuck inside our radical forever, like it's in jail. So 5 times the square root of 5 would be our answer. Let's look at a couple more. Sometimes we have variables under our radicals. So if we have variables under there, it's the same type of thing. We're just going to look for groups of 2. So we're going to split A up. A cubed would be the same as having A times A times A. So we have one group of 2. 16, remember, is 4 times 4. So we could really write this as 4 squared times A squared times A. And now we can simplify. Well, the square root of 4 squared is just 4. The square root of A squared is just A. And we can't take the square root of A by itself, so that's just stuck inside the radical forever. 4 times A times the square root of A is our answer. be a good idea to pause the video and try f. Well, we already have x squared, so we're just going to leave that. But y to the 5th, we're going to write out 5 y's and see how many groups of 2 we have. We have 1, 2. So we could write this as the square root of x squared times y squared times y squared times y. Well, square root of x squared is x, square root of y squared is y, square root of y squared is y, and this y is just stuck in our square root forever. Notice how we have these 2 y's outside of our radical, so we can multiply those together and use our exponent rules to write them as y squared. So our simplified answer would be x times y squared times the square root of y. We also have something called nth root. So all of these were squared roots. This is the most common. Anytime you see this symbol, that's going to be a square root. But we could have a third root or a fourth root or a cubed root. You just have to change the index. So that'd be a cubed root, a fourth root. You could take a 100th root if you wanted to. You just have to change the index. So here we've got cubed roots, and notice how they have that index of 3. So you can try A if you want, but we're just going to do letter B together. So we've got 81, we could write as 9 times 9. And then we'd have 3 times 3. P to the 5th, we could write out 5 p's. And q to the 3rd, we'd write out 3 q's. Well, since it's to the 3rd index, we're looking for groups of 3. So here's a group of 3, here's a group of 3, and here's a group of 3. So we could write this as the cubed root of 3 cubed times, I'm going to rewrite this, 3 cubed times 3 times p cubed times p squared, because there were 2 of those left over, times q cubed. And notice how there are no q's left over. And now we're going to simplify. So just like the square root is the opposite of squaring, the cubed root is the opposite of cubing. That's why we looked for groups of 3. So the cubed root of 3 cubed is just 3. Well, this is not a group of 3, so it's stuck under our radical. The cubed root of p cubed is just p. P squared, again, it's not a group of 3, so it's stuck under our radical. And the cubed root of q cubed is q. So this would be our simplified answer. So that's how you look at cubed roots. Fourth roots, it's the same type of thing. You would look for groups of 4. So we'll just do letter A. You can do a letter B for a challenge if you want. So 64 we could write as, let's see, 8 times 8 is 64. So 4 times 2 is 8, 4 times 2, 2 times 2, 2 times 2. So we're looking for groups of 4. So here's a group of 4, and then we have 2 extras. So we could write this as the fourth root of 2 to the 4th power times 2 squared. Well, the fourth root of 2 to the 4th power is just 2. We can't take the fourth root of 2 squared, so we could just leave that in our radical. But I'm actually going to evaluate that. So our final answer would be 2 times the fourth root of 4. And that would be our answer. So basically, whatever your index is, you look for groups of that, and then your index and your exponent will cancel each other out. And that is the gist of our square roots and our nth root.